White dwarf. White dwarf stars are believed to represent the final evolutionary state of stars that are not massive enough to end their lives in super or hypernova events, also known as degenerate stars. White dwarf consists of electron-degenerate matter that no longer produce fusion energy. Instead, white dwarf stars radiate their stored thermal energy as a faint luminosity, but so slowly that the universe has not existed long enough for any white dwarf star to have emitted all of their heat. Hello and welcome to the world of astronomy. This is Akash, and today I'm discussing some important facts about a white dwarf. Actually, a white dwarf is the final stage of a star when the star ends and all of its energy is used. There is no more fusion. Point number 1. About 97% of all Milky Way stars will become white dwarf. While only 10,000 or so white dwarfs have been found, more than 97% of stars in the Milky Way, including the Sun, are not massive enough to becoming anything else than white dwarf stars when they end their lives. Taken to extremes, this means that once all the stars in the Milky Way have evolved into white dwarf and have cooled down sufficiently to become black dwarf, the Milky Way will, for all intents and purposes, become invisible, except perhaps for the few neutron stars that may outlive both the white dwarf and the dispersion of the galaxy. Point number 2. Almost all white dwarf stars have the same mass. While white dwarf stars fall into a wider range of masses, from as little as 0.17 to as much as 1.3 times the Sun's mass. Most white dwarfs weigh in between 50% to 70% of Sun's mass, with an average of around 60%. In practice, this means that while white dwarf stars are typically about as big as the Earth, they are in general terms about as massive as the Sun, meaning the density of the white dwarf can be as much as 1 million times higher than that of the Sun. This in turn means that the 1 cubic centimeter of white dwarf can weigh as much as 1 metric ton, with only black holes, neutron stars, and possibly quark stars being denser. Point number 3. White dwarf stars cannot exceed 1.4 solar masses. Due to the nature of degeneracy pressure, which is what supports a white dwarf against gravitational collapse into a neutron star, a white dwarf can never exceed 1.4 solar masses, a limit that is known as Chandrashekhar Limit, after the Indian astronomer who first calculated the limit in 1930. However, this figure assumes that the star is not rotating, but if it does, the limit increases slightly. Nonetheless, in cases where a white dwarf is rotating in a non-uniform manner and the viscosity of the star is not taken into account, there is no upper mass limit at which a hypothetical white dwarf can be in hydrostatic equilibrium. Point number 4. White dwarf stars cool down more slowly as they age. Studies have shown that since white dwarf stars do not generate energy to replace the heat that is lost through rotation, the rate at which these stars cool down slow as they age. The following example illustrates the point. A white dwarf with a mass of 0.59 times the mass of the Sun, that has a helium atmosphere and a surface temperature of about 8,000 Kelvin, will take around 1.5 billion years to cool down to 7,140 Kelvin. Cooling down at another 500 Kelvin will take about 0.3 million years. while cooling down to 6,000 Kelvin, and then another 500 Kelvin will take about 0.4 billion and 1.4 billion years respectively. Point number 5. White dwarf stars have atmospheres. Spectroscopic studies have revealed that much of a white dwarf star's luminosity derives from its atmosphere, which can consist of either hydrogen or helium. While both elements are usually present in the atmosphere of white dwarf, one always predominates by a factor of at least 1,000 as compared to all other elements in the stellar atmosphere. Most investigators agree that this is the result of a process in which gravity separates the elements in the atmosphere, with the most massive molecules accumulate at or near the surface of the star, with the lighter element stacked onto this layer in the order of their mass. In case of hydrogen-rich atmosphere, the total mass of the hydrogen component may be as massive as 1/10,000 of the star's total mass. Point number 6. Some white dwarf stars are metal-rich. The fact that the spectra of some white dwarf stars show strong metal lines came as a surprise to astronomers, since these heavy metals should have gravitated towards the star's core soon after its formation. While there is no certainty as to the origin of the metals in some spectra, it is thought that in the case of white dwarf designated DUN 345 at least, the metal abundance in its spectrum derives from the remains of a planet that were destroyed by the progenitor star during its asymptomatic giant branch phase. Point number 6. White dwarf stars will outlive their host galaxies. Although white dwarf stars are considered to be stable after their formation, they will eventually cool down to become cold-black dwarfs. However, due to the opacity or resistance of their outer layers to radiation, it is estimated that the white dwarf will take around 10 to the 34 to 35 years to reach this stage, and this exceeding long lifetime is based on the known lifetimes of protons, which is far longer than it takes for galaxies to disperse or evaporate, which process is expected to be complete in a mere 10 to the 19 to 10 to the 20 years. Point number 8. Some white dwarfs host planets. While there is some debate as to how planets may form around white dwarfs, many white dwarfs are nevertheless orbited either by planets, as in case of two circubinary planet around a curious white dwarf or red dwarf binary system designated N Serpentis, or by dense dust debris disks. Most investigators subscribe to the theory that planets orbiting white dwarf are the remains of planets that were destroyed by the creation of the white dwarf, such as would happen when our sun swelled up during the red giant phase. In our case, Earth might end up as a disintegrating rocky body orbiting the sun in its white dwarf phase. Point number 9. White dwarf stars can explode several times and yet survive. While some processes can destroy a white dwarf star in a supernova explosion, many white dwarf stars survive repeated but less cataclysmic thermonuclear explosions of accelerated hydrogen-rich material on their surfaces. Provided the star's core remains intact, a white dwarf can survive as many explosions on its surface that it takes to deplete this source of an infalling material. So this is all about white dwarf. If you want some more videos, please comment, share and like. Thank you very much. Have a good day. Bye bye.